So here are the two bits of sophistication that we don't have yet, but we would like to have by the end of the hour today. First of all, is there a way to determine the rate of change of one quantity with respect to another, not between two different points in your data, but rather at a single point? Instead of in between 2 points, we want to talk about the rate of change at a single point. In other words, this rate of change that we speak of today is not an average rate of change over an interval, but is instead an instantaneous rate of change. I spelled it wrong. Instantaneous rate of change at a single point in your data. So instead of connecting two different points on a graph, if you like, we're going to look at a single point only. This is the biggest change in sophistication, and to really tell the complete story of what this means, we would need more time, and we would need some more concepts from calculus. Those of you that have had exposure to calculus, or who will in the fall, will recognize what we're talking about today as being a derivative. The derivative in calculus refers to this concept of instantaneous rate of change. So that's the first piece that we need. The second piece that we need is, if we're going to do this, if we're going to find the rate of change of a function at a single point, it is not enough for us to do it from a set of data. Why? Well, because in order to get the rate of change at a single point, we would need to know, let's say we wanted to know the rate of change of this relationship, which is up here, the relationship between the height of a cannonball that we fire and the length of time since it was fired. So we fire a cannonball out of a cannon somehow, and its height, measured in meters, is related to time in seconds. And if I want to know 6 seconds after I fire this cannon, t equals 6 seconds, say, what is its rate of change, what's its upward or downward velocity, I would need to have a couple of points that are so close to one another that they're practically indistinguishable. In other words, in order to find the instantaneous rate of change at a single point, t equals 6, I would need to have not only a point of data at t equals 6, but I would also need to connect it, quote unquote, to another point which is so close to t equals 6. Let's say it's that close. So it's really, really close to t equals 6. And somehow, be able to compute the rate of change between those 2 points. Problem is that data is not that friendly. First of all, that this data table that I have down here at the bottom is measured at 2-second intervals. So every 2 seconds we know what the height of the cannonball is. And 2 seconds is kind of way too much length of time to be able to tell an instantaneous story at a single point. In fact, from a calculus perspective, even this really, really close together point, 6 point, a whole bunch of zeros and then 1, is still too far away from 6 to tell the whole story. So in calculus, the concept of a limit is what saves the day. And we're not going to talk about limits in our course. But that's, when you get to calculus, really what's going to happen is that we're going to take what calculus folks call a limit as this second point gets infinitely close to the first. And I'm going to put that in quotes as well. But that's in principle what we need, infinitely close to t equals 6. But we can't get infinitely close with a number, because there is no number that is closer to 6 than any other number besides 6. The real numbers are dense in that way, so we can't do it with a number. So that means that we also can't do it with data. No matter how well-intentioned our data set is, no matter how close together our observations, data is not enough. Instead, we want to do it with formula. So the name of the game today is to tell a rate of change story not beginning from a set of data, but instead beginning from a formula that models that set of data. So in this example that we want to start the hour with today, we're given a formula that relates the height of this cannonball, h, measured in meters, to the length of time since it was fired. So it was fired at t equals 0 seconds by assumption. And we happen to know its height as a function of time. So at every different moment in time, we know how to compute the height of this cannonball. And here's a list of questions I'd like for us to be able to answer. So I want your groups to begin with these. is, first of all, how do we know what height the cannonball was fired from? In other words, when the cannonball left the cannon at that instant in time, what height above the ground was it? And then questions B, C, and D relate to its velocity. And when I say velocity in this question, I really mean upward or downward velocity, not the vector velocity as a physicist might think about, but the upward velocity. In other words, the rate of change of height with respect to time. And if that's positive, then we have a cannonball that's going up. If it's negative, we have a cannonball that's falling. So we want to answer these questions. What was the cannonball's velocity at time t equals 0 seconds? What is its velocity at any arbitrary point in time t? And then at what point does this cannonball stop going up and start coming back down? So that's what we'd like to answer. And we want to ultimately not do it with data, but instead do it with formulae. Start from the data and figure out what was the average rate of change of height with respect to time at a variety of these data points. And we'll use a symmetric difference, so we won't be able to do it at either end, but we will be able to do it at times 2, 4, 6, and 8. How would I find, for example, what is the average rate of change of height with respect to time at t equals 2 seconds? How do you compute that average rate of change? Since we're using a symmetric difference, take the points that are on either side of 2 and find the slope of the line segment that joins those 2 points. In other words, find the rise, which would be the change in our height values here, our delta h. That's 243.6 minus 2. So that's 241.6. And then find our run, 4 minus 0. And then just divide the former by the latter. 241.6 divided by 4. That's 60.4. And the units of that 60.4 will be, what would the units of dh dt be here? Right, h is measured in meters, t is measured in seconds, and so this is 60.4 meters per second is the average rate of change. We'll do that for t equals 4, 6, and 8. All right, so there are our average rates of change at these 4 different points in time, 2, 4, 6, and 8. But now, something we notice about these average rates of change. First of all, what is the trend in these average rates of change? What are they doing as time goes on? They're decreasing. In other words, the upward velocity, the velocity at which this cannonball is rising, starts out as positive because the cannonball starts out going up, because we're firing it in an upward direction. But its upward velocity is decreasing because why? What's the physical reason that the upward velocity would be decreasing? Gravity. Right. Because there's an acceleration due to gravity that's negative, it's tending to decrease the upward velocity of this cannonball. So first of all, we notice that the velocities are decreasing. Well, let's take a closer look. How are these velocities decreasing? By how much does this velocity decrease between time t equals 2 and t equals 4? That's 40.8 minus 60.4. 19.6. Is it? I think it's 20.4, isn't it? Unless I'm turned around. 40.8 minus 60. Oh no, you're right. Yeah. Sorry to have doubted you. 19.6. So 19.6. How about from the next time period to the next time period? 40.8 to 21.2. 19.6. Uh-oh. And the next time period, 19.6. So not only are these velocities decreasing, they're decreasing predictably. Every 4 seconds, the velocity is going down by 19.6 meters per second. So what that tells us is that this velocity, dh dt, versus time is what kind of a function? We have the same amount of change in dh dt every time we have the same amount of change in time. What kind of a relationship is that? Linear. And this is the key observation, is that if this really is a linear relationship, we should be able to write an equation for it. We should be able to find a slope and an intercept of the relationship between dh dt, the velocity, and t, the time. Let's try it. What is the slope of this relationship between dh dt and t? How do I find it? Remember, a slope is just a change in one quantity divided by the corresponding change in the other quantity. Negative 19.6 divided by 4. What is negative 19.6 divided by 4? Negative 4.9. So there's the slope of this relationship. Wait a minute. No, sorry. 4 is the wrong thing to divide by. My fault. These 19.6s corresponded to changes between time t equals 2 and t equals 4, between t equals 4, t equals 6, t equals 6, t equals 8. In other words, instead of dividing by 4, we're really dividing by 2. So, my fault. Divide that by 2, the slope is negative 9.8. And let's see if we can find the intercept. To find the intercept, all we need to do is write out the equation that we have in slope-intercept form so far. Negative 9.8 is the slope times t plus some intercept. And then we'll just plug in a point. Let's say we plug in the point where time is 2 seconds and velocity is 60.4. When I plug that point in, we can find the value for this intercept. 60.4 equals negative 9.8 times 2 plus b. Negative 9.8 times 2 is negative 19.6. And then adding 19.6 over to the left side, 60.4 plus 19.6, 29, that's 80.0. So in other words, here is an equation that can tell us the velocity of this cannonball at every instant in time. And dh dt, we're going to rename it at this point because it looked like an average rate of change. What we're going to do is just replace those deltas with d's, straight plain old letter d's. And we're going to call that the instantaneous rate of change, i.e. the derivative. Now, we took a very long route to get this. It took a lot of luck and observation and computation, right? We had to first compute the average rates of change in our table. Notice that the average rates of change had a predictable pattern to them, and in this case, that pattern happened to be linear. Once we know that pattern is linear, then we can find an equation for that linear relationship by discovering the slope and then plugging in a point to find the intercept, and that is a lot of work to do. Even though our result is really useful, okay, and it's worth spending a lot of time getting this result, we don't want to have to do that every time. I know you don't, especially if I ask you to do this on an exam. That's too much work. And it won't always work this way. That's the other thing. So what we need to do then is figure out what is the relationship between the original formula for the height and the formula that we have here for the instantaneous rate of change of the height, which we call the velocity, the upward velocity. What is the nature of the relationship between these two formulas? So let me just write them one above the other, and we'll talk our way through it. So on the one hand, h is negative 4.9 t squared plus 80 times t plus 2. On the other hand, the velocity, dh dt, was negative 9.8 t plus 80. Those of you that watch the videos for today will already know the answer to this, or if you've had exposure to calculus before, you'll also know the answer to this. But let's go one term at a time, starting with the term the farthest to the right, starting with this 2. What happens to this 2 when we pass from the original function to its derivative? Where did it go? It went away. So the first observation we can make here is that anything which is constant, any portion of your formula which turns out to be a constant, like the number 2 in our example, that when we take the derivative, the instantaneous rate of change, the derivative of a constant is 0. So that constant, the number 2, when we took the derivative, when we passed to the derivative, that constant goes away. It just vanishes. Why? Because constants, by their very nature, do not change. So the instantaneous rate of change of a constant quantity is nothing. It doesn't change. So the derivative of a constant is 0. So that's for the first piece. The next piece is this one, the linear term. The 80 times t turns into 80. How would you describe what's happening there? The derivative of a constant times t. How would you describe to somebody what process is happening there when we take its derivative? The derivative of, okay, the derivative of a first power variable, in this case that's the t by itself, right? T raised to the power 1. Okay. That the derivative of that portion becomes just a 1. This is the rule that we're going to be generalizing in a moment. So t to the power 1, when we take its derivative becomes just plain 1. Now let's look at the very last term to the left. This one right here. Negative 4.9 t squared becomes negative 9.8 t. So what would you say, let's forget about the negative 4.9 out in front for a moment. What would you say is happening to the t squared? So we started with an expression that has 2 powers of t in it. We ended up with something that has how many powers of t in it? Just the 1. So the first observation is that the number of powers of t is going down. Notice that that also happened in the last example. That when we started with 1 power of t, we ended up with no powers of t. So the number of powers of t goes down by 1 when you pass to a derivative. So that's the first observation. The second observation is this time what is happening to the coefficient, the number that's out in front, negative 4.9. What's happening to it? It's being multiplied, yeah, you're looking ahead. It's being multiplied in this example by 2. But why 2? Because 2 is the original power. And that's the overarching rule, which again, without calculus, we can't prove why this is true. As scientists, we could compile a bunch of evidence for it. But it would really take a little bit more mathematical rigor to show why it's true. But this is called the power rule in some calculus classes. Power rule. And the power rule says that the derivative of t to the power n, derivative, is, first of all, that power, as Eliot says, that power multiplies out in the front. Okay. And then the exponent is decreased by 1. N times t to the n minus 1. So I like to think of it as a 2-step process. The first step in the process being to multiply by the exponent, whatever the exponent happens to be. And the second step being to decrease that exponent by 1. And that's how we take a formula for a quantity and turn it into a formula for its instantaneous rate of change, which we call the derivative. Anytime we're looking at a formula that is built out of powers of t, we can use this power rule. That includes not just powers, integer powers of t, like t to the second, t to the fourth, constants, t to the first, but it also includes things like the square root, which is a 1/2 power of t. Also things like reciprocals, 1 over t, that's t to the -1 power. So there are a lot of different kinds of functions that don't look like powers when we first write them, but which we can turn into being written as powers of t. And then this process can help us to find the rate of change function, the derivative, of that expression having powers of t.